Good evening, everyone. I'm Ranthu Chakodi. As it's a golden moment in the world history, you can find out more about the James Webb Space Telescope and watch the telescope launch live on our YouTube channel. First, let's see what astronomers have to say about the Webb telescope, James Webb Space Telescope.
A long time ago, all we could do was look up at the stars and wonder what they were. Then we learned, with the help of telescopes and technology, to extend our human senses farther. Farther than those first humans could ever imagine. But we haven't reached the end yet. We know there are more wonders out there. We know there is farther yet to see. If we are seeking new views of our universe and discoveries that we can barely imagine today, we need a completely new way to see. Humanity needs to open fresh eyes to see our universe in a way we never have before. Welcome to NASA's Goddard Space Flight Center. I'm Michelle Thaller. In just a few weeks, NASA and its European partner, ESA, will launch the James Webb Space Telescope, a colossal leap forward in humanity's quest to understand our place in the universe and our part in a story that stretches back to the beginning of time. Today, I have the great privilege of hosting a conversation about the inner workings of the Webb telescope, the largest and most ambitious observatory ever launched into space. While the science goals of Webb promise the beginning of a new understanding of our universe, the technology of Webb is a marvel in itself. And so to get this conversation started, I'm joined by Eric Smith, the program scientist for the Webb telescope. Good to be here with you, Eric. I'll put my mask on.
Yeah.
That's right.
Hi, Michelle.
Hi.
It's great to be here.
Absolutely. Tell us a bit about the history of Webb and how it fits in.
Sure. Well, actually, to continue this story about how telescopes and that technology change our view of the universe, I actually want to start in the 1840s with a telescope that was known by the fantastic name of the Leviathan of Parsons. A comparison of what the Earl of Ross drew in 1840 to Hubble's view of M51 galaxy. So Hubble itself tries to find these first galaxy more amazing instruments. That's the James Webb Space Telescope. So not only will it help us complete this chase of galaxies, but it promises to allow us to explore the atmospheres of exoplanets, alien worlds, study how stars form in our own galaxy. And today you'll hear about this amazing telescope and the instruments that will make that all possible.
That's absolutely wonderful. Thank you so much for joining us, Eric.
My pleasure.
So as we talk about the instruments, one of the first things we need to do is talk about this amazing giant mirror. And there's nobody better to speak to us about that than Lee Feinberg. He is the optical telescope manager for Webb here at Goddard Space Flight Center. So Lee, talk to us about the incredible mirror that all these instruments will use.
Well, at 6.5 meters, the primary mirror was too big to fit in a rocket. So we designed it so that it would unfold in space, and it does it like a drop leaf table. But in order to do that, we needed mirrors that could be in segments. And so we've designed the segments to be hexagonal shaped. And that's really nice because all 18 mirrors have the same mechanical design. So we get a lot of economies of scale in how we made the mirrors. And they're actually made out of beryllium. And beryllium is really ideal for these very cold temperatures. So that's why we chose beryllium. And we coat them with gold, a very thin layer of gold. But gold is ideal for the infrared wavelengths, very high reflection. And that lets us see as far as we can and capture all the photons.
It's absolutely wonderful. Is there anything else you'd like to add about the mirror before we go?
No, I mean, the mirror on Webb is actually much larger than previous space telescopes. In fact, it's lighter as well. The primary mirror for the Hubble Space Telescope is 10 times heavier per unit area. So we had to make a much lighter mirror. And this mirror is also, if you compare it against like an infrared telescope, like the Spitzer Space Telescope, which NASA launched many years ago, the Webb telescope is actually 50 times larger. So it has a lot more ability to collect photons, and that makes it much more sensitive. Yet it actually works at shorter wavelengths than the Spitzer Space Telescope, almost down to the wavelengths that Hubble works at.
Absolutely excellent. Well, thank you so much for joining us, and we'll see you for the questions later on.
Okay.
All right. So the next person who will be joining us is Marcia Ricci. And Marcia Ricci is the principal investigator for the NIRCam instrument. So she's actually speaking us today from the University of Arizona. So Marcia, are you joining us?
I'm here and very happy to talk about NIRCam.
Please go ahead.
Okay, well, NIRCam is a dual-purpose instrument. It is both a science camera and the wavefront sensor. So as Lee mentioned, the telescope mirror comes in 18 segments and they have to be aligned. And so you can see NIRCam is also dual in the sense of how it was constructed. It has two identical halves bolted together, and that gives us the redundancy so that NIRCam can always be available to align those mirror segments. And this is a big advantage for deep surveys because we can look at twice the sky. And what you're also going to see is a light sensor package, aka detector package, in the test tour here on campus where we gave it its final run through. It has 16 megapixels, with the full instrument having 40 megapixels, which is a lot of pixels for sitting a mile away, a million miles away from Earth. Now, you might ask, what are we going to do with all those pixels? And we have several very big science projects that we're going to do. One of the things that was part of the original plan for the telescope is to look for the very first galaxies to form after the Big Bang. And we know, and here you can see the Big Dipper, and we're going to zoom in to the kind of image that Hubble took as best it can do on these very distant, very red objects. And shortly, a red blob will appear, and that red blob, we're seeing the light from this galaxy as it left only 400 million years after the Big Bang, about 3% the age of the universe. This particular galaxy is extremely bright, and we think it's only the tip of the iceberg of the kinds of galaxies that Webb is going to detect, and we hope we get even closer in time to the Big Bang than what this galaxy is. Now, looking for distant galaxies is not the only science that NIRCam can do. It can be used for many projects, including looking at the atmospheres of planets orbiting other stars, exoplanets. And the way we're going to do that is using the transit technique. And so what we'll do is we will observe a star, a planet will pass in front of it, and the light from the star will be dimmed for a little while. And then if we analyze how that light gets dimmed and look at what colors of light come through, we can analyze the pattern and see what kinds of molecules are in that atmosphere. Now, that's not the only way that we can observe exoplanets. We also have the capability to look at them what we call directly, that is, in the light that they reflect from their parent star. And ordinarily, you can't see these planets. Here's a hypothetical rocket ship going through this exosolar system, and when you're actually there, you can see the planet. But if you move far away, like our vantage point with then it gets lost in the glare of the sun, and you have to blot out the starlight using a dark opaque disk that we call a coronagraph. And so that's just a quick sampler of the things that we'll do with NIRCam.
Now, of course, JWST is not just an imaging camera, but it also has a lot to do with spectra as well. So now we're going to Pierre Fruy. He's actually the NIRSPEC principal investigator from the European Space Agency, and it's a spectroscopy technique. So Pierre, welcome to our broadcast.
Yes, thanks, Michelle. I'm very happy also to be here, to be able to talk about NIRSPEC. So NIRSPEC, indeed, its name means near-infrared spectrograph. So it's a spectrograph, and it's part of European contribution to Webb, like the mid-infrared instrument. And NIRSPEC is going to allow to probe a wide variety of astronomical objects, from the first galaxies to planets orbiting over stars. And with NIRSPEC, it's going to be achieved by analyzing spectra and not images. And NIRSPEC is a pure spectrograph. So we are all used to images, but spectrographs work a little bit differently. They are going basically to take the light from an object, as you can see on the screen, and split it into its component, creating what we call a spectrum. And spectra contain information about what the object is made, what are its physical, its chemical properties. So it's a treasure trove of information that NIRSPEC is going to put in the hands of scientists all around the world. So all JWST instruments have spectroscopic modes. As you have already heard for NIRCam, you will hear for NIRISS, and it's also the case of MIRI. And NIRSPEC is going to offer additional choices to Webb scientists. If I take one example, if we take the little red blob that Marcia presented, these very distant galaxies, they are so far away, they are located more than 13 billion light years away, that very little of their light is going to reach us. So to observe them, we are going to have to stare for hours. And this is why NIRSPEC is really designed to observe more than 200 of them at the same time, not one. And it's a very efficient use of Webb's precious time. To do that, it's equipped with a very special novel device that you see currently on the screen. These are arrays containing close to 250,000 of very tiny little doors that you can open, close at will. And to observe with NIRSPEC, scientists will pick a patch on the sky, select the objects, open the doors in front of these objects, close the doors for the others, and they will get individual spectra for this object, close to 200 at once. Okay, and that's the first example. And you will see another example for NIRISS of observing multiple objects at the same time. But sometimes scientists actually are not interested in getting 200 spectra of 200 different objects. What they want is to get as many spectra as possible from one object. And NIRSPEC can do that, like MIRI, in fact, and it's going to use what we call a slicer. It's going to slice the image of the object in 30 slices. You're going to see on the screen this image of a galaxy, and you cut it not 30 here, but in NIRSPEC it's 30. Each of these 30 slices is going to give you 30 spectra. So 30 times 30, it means you get 900 spectra at once of a given object. And with that, you are able to map beautifully the physical, kinematical, chemical properties of an extended object, a nice object like a galaxy. So that was basically to give you an overview of what can NIRSPEC do. Of course, NearSpec together with NearCam, with MIRI, with NIRIS, is going to offer really a very nice toolbox to scientists, a spectroscopic toolbox. And to conclude on this image, which was when NearSpec was fully assembled, really now we are ready. Now we are in JWST, we are ready, and we are waiting eagerly for launch and to.
Thank you very much, Pierre. So in keeping with our theme that this is a very international collaboration, we're now going to Canada. And so for our last guest, we're talking to René Deon, and he is at the University of Montreal. René, please tell us
Bonjour,
about...
Michel. I'm very glad to be here. So I'm going to talk to you about the Canadian. So the Canadian Space Agency is providing two key elements built by ComDev that are now known to be Honeywell. So I'm going to talk about the fine gathering sensor, which is the gather for short. So the gather is not a scientific instrument, but nonetheless a key component of the observatory. So the gather is basically an infrared camera that look at the sky and pick up a star, and we track its movement while we take any observations with all science instruments, because there's inevitably vibrations, and if we don't correct for them, then the images would be blurred. And so what we do, we send a signal to the fine string mirror, a small mirror inside the observatory, that we can tip and tilt 16 times per second, and we can that way get the best possible, sharpest images. And just to give you an idea how accurate the gather is, where the gather will be capable of measuring an angular displacement of the telescope equivalent to the thickness of a human hair as seen from 1 kilometer. Or if you want, it's like being able to see someone blinking from New York City, in New York City from Washington, D.C. So it has to work that accurate to get the best possible images. So on the backside of FGS, we have the scientific module of the Canadian instrument called NIRIS, which is Near Infrared Imager and Slitless Spectrograph. So NIRIS is basically an infrared camera operating on the same wavelength range as NearCam and NearSpec, but and can take images like NearCam, but mostly will be used for spectroscopic observations that Pierre described so well, and also Marcia. So in one mode, we're going to be doing transit spectroscopy that Marcia described very well, but our mode is specialized to look at very bright stars. We can disperse light over a wide wavelength range, but at the same time, making sure that we don't saturate our detector with a very special prism that will allow us to look at planets like the TRAPPIST-1 system. So here's an animation that they illustrate the technique. We're looking after the tiny sliver of light that forms the atmosphere that is filtered by the starlight. This is very difficult to do. We can do that with Hubble. Well, we're going to be able to do it much better with Webb. So we'll look at a target like TRAPPIST-1. This is the rock star of a planetary system, a system that has 7 planets transiting its star, and 3 of them are right in the habitable zone. So those planets could have life. So the big question is, do these planets have an atmosphere? And we're sure going to be looking for those planets and be able to say whether they have water, CO, and methane in one single spectrum that NIRIS will be able to take. Now, let me move to a second mode, and we move our filter wheel and we put another prism. This time we're going to do slitless spectroscopy. So it's just like NearSpec, but instead we take spectra of everything in our field of view. Now, this is a picture of our filter wheel, and one of them has prisms. These are dispersing elements, allowing just to take a spectra. And one special target we want to look at are galaxy clusters. Those are, we're interested in studying the galaxy and the cluster themselves, but we know that these clusters have also hidden mass, dark matter, and that cluster just act like a gigantic cosmic telescope. And we hope to be able to detect very distant galaxy that happens to be behind the cluster, and using the magnification aspect of the cluster to detect those very faint galaxies. Now, slitless spectroscopy is not as efficient as doing slit spectroscopy, but the advantage is that you get everything in the field of view. So in one shot, we'll take spectra of 3,000 galaxies, so about 30 times or 20 times what NearSpec can do. Less efficiently, of course, but we may find some very very distant galaxies, and then tell near spec, Miri, go here, put your slit here, and let's take a spec on all these very high distant objects. And finally, and not least, we have another mode in NIRISS that called aperture masking interferometry, which is basically inserting a mask inside the filter wheel that will block most of the light of the telescope, which is kind of strange, right? But will take the light of only 7 segments. And that way we'll be able to detect very faint companion close to the star, well within the dark spot that Marcia was mentioning. And so we're going to be able to detect new exoplanets, young gas giant planets, or planetary system, young planetary system like the one we've just shown. We're absolutely excited to get NIRISS on the sky, and we can't wait for the launch.
Thank you very much, Renee. So it's been a long journey to get ready for the launch, but it pales in comparison to this great journey ahead. Webb needs to travel 1 million miles away from Earth before it can even begin its quest for ancient light. That rocket road trip begins at an extraordinary facility located in Kourou, French Guiana. The Guiana Space Center is a tropical facility, but it's also a gateway to the stars. Few spaceports on Earth have soundscapes that include the roar of rockets, followed by the sounds of tropical jungle, once rising spires of fire disappear above the clouds. Once Webb's Ariane 5 leaves the launch pad, flight control transfers to the Mission Operations Center in Baltimore at the Space Telescope Science Institute. It's here where mission managers will not only control the spacecraft, but also gather data from the telescope science. Scientific instruments. So we're going to take a quick break now, and when we come back, we're going to be taking live questions from the media. If you have questions of your own on social media, you can use hashtag #NASAWeb. So join us in a few minutes, and we'll be back to actually talk to this extraordinary panel of scientists and engineers about the inner workings of the Webb telescope.
Our universe is a wild and wonderful place. In NASA's Curious Universe podcast, NASA is your tour guide. Join astronauts, scientists, and engineers on a new adventure each episode. Investigate black holes. Spend a day on the International Space Station and meet the experts behind the revolutionary James Webb Space Telescope. Find NASA's Curious Universe in your favorite podcast app or by visiting nasa.gov/podcasts.
What's out there? Let's find out. The James Webb Space Telescope Augmented Reality app. Whoa! Check out the most extraordinary scientific instrument ever designed in your own space today, only from NASA.
Welcome back to the James Webb Space Telescope pre-launch briefing. I'm Michelle Thaler, and we're here at NASA's Goddard Space Flight Center. What we're going to do now is take live questions from the media. And on social media, if you have questions of your own, just join us at hashtag #NASAWeb. So at this time, I'm going to ask the operator, do we have the first question for our panelists?
Yes, thank you. At this time, for phone line, it is star followed by number 1. Should you have a question, please unmute your line and record your name clearly as prompted. Again, with phone line questions, it is star followed by number 1. And our first question is from Bill Harwood. Your line's open.
Hey, thank you very much. Bill Harwood, CBS News. For Eric or Lee, maybe, I'm not sure, but can you provide some detail about how you get Webb into focus? I'm interested in how you'll use NIRCam, I guess, to position each mirror segment, how the position actuators work, how that one works that can change the shape of a segment slightly if necessary, and just how that process works out to bring those 18 individual images down to that one diffraction-limited image. Thanks.
Yeah, sure. So when we first start, when we get the very first light from Webb, which we'll be using the NIRCam instrument, the primary mirror segments are actually highly misaligned by millimeters. And so they actually act like 18 separate telescopes. They share a secondary mirror, but it's essentially like we'll get 18 images of a star when we look at just one bright star. And so our goal will be to first align those individual telescopes and then put them on top of each other. We'll take those 18 spots, we'll put them right on top of each other, but each of the telescopes are still not what we call phased up. And by phasing, I mean we have to improve the alignments by a factor of 1,000,000 so that the entire primary mirror is aligned as though it's within about a 5,000th of a diameter of a human hair. And we have a series of algorithms. It actually takes several months to do this. We start with algorithms that are easier to do, like moving the mirrors around. But as we get towards the end of these algorithms, we actually borrow a couple of algorithms, one from the Keck telescope, which does the phasing that gets us within a wavelength of light. And then at the very end, when we get the final curvature of the mirror, we're actually using an algorithm that was perfected when we were trying to determine the prescription of the Hubble spherical aberration problem. So we've borrowed from previous telescopes, and we go through the sequence of algorithms, and about 120 days in, we should have an aligned telescope.
Wonderful. Okay, we're now going to go from questions from social media. This is a question about, I believe this was probably going to NIRCam, because the question is, how clear will Webb's pictures of Mars be? And so, Marcia, was that one that you could answer, about the clarity of images of planetary objects like Mars?
I can answer that in part. One of the big challenges is that Mars is actually very, very bright in the infrared. And so if we want to take an image, we have to take a series of quick snapshots of just a little portion of the disk and then stitch them together. And a complication is that Mars rotates while we're taking the picture, but some schemes have been worked out, and I think when we get to the outer solar system, planets like Uranus and Neptune will be much easier to do, but they will give us images that will rival what we've seen from the Voyager flybys, but being able to do it in the infrared, we'll be able to trace out some of the molecules in those planets' atmospheres, things like methane. So we'll be able to look at Mars, but it takes a lot of effort because of how bright and how quickly it rotates.
All right, as far as some more questions from social media, I guess this one is actually one that we could have answers both with spectra and with images. The question is there a possibility to look at Oumuamua as it continues its journey away from the sun using the James Webb Space Telescope? Oumuamua was a comet that actually we believe came from another solar system. And there are more of these objects that we're going to find with the Webb. Can anybody answer the question about information on interplanetary comets, intersolar system comets?
I think if we have an adequate orbit, we could point, but I don't know if we know its orbit well enough to be able to point to where it has traveled to now in space, because it spent such a short time in the solar system, it kind of whizzed by. And whether we know exactly where it's going accurately enough to point Webb, I'm not sure.
Thank you. Would anybody like to add anything else, or shall we go move on? Okay. So the next question I believe we have is from the media. The operator?
Thank you. Our next question is from Irene Klotz. Your line's open.
Thanks very much, Irene Klotz with Aviation Week. I had a question about imaging these earliest structures after the Big Bang. Are scientists dependent on gravitational lensing with JWST, or is that something that JWST will be able to see directly?
Eric, would you like to take that?
I can
answer. Sure. Marcia, please go ahead.
Right. We hope to be able to image these very distant galaxies directly without the help of gravitational lensing. And if there are ones even only a hundredth as bright as the one that I showed in the video, we'll be able to do a lot. But the virtue of gravitational lensing is that it magnifies. And so if we think about whatever ones we can see directly with NIRCam, we could go after somewhat fainter ones using gravitational lensing. So we may learn the most by combining just straightforward imaging on a blank piece of sky with something that's been gravitationally lensed.
Eric, did you want to add anything to that?
No, I was going to say exactly what Marcia said. We'll do both things
Absolutely.
with Webb.
All right. So our next question is from the news media. Please go ahead.
Bill Harwood, your line's open.
Oh, thank you very much. I think this is for Marcia, but you know, I realize that spectra are key to Webb's operations, but the public will inevitably compare Webb's pictures with Hubble's, which, you know, everybody's familiar with. How will the images from this infrared telescope compare to what we're used to seeing from Hubble? I realize you've been asked this a million times. I'm just asking it one more. Thanks.
Well, in terms of the level of detail that we can see, we'll be able to see as fine a detail as Hubble, even though we're working at much longer wavelengths. But what's going to be dramatically different is using the infrared, we see things very differently. So if you think about the image of the pillars of creation that you get from Hubble, if you take a similar picture with NIRCam, you will see through those pillars, the dust will basically disappear and you'll see stars inside. And if you go a step longer and look with MIRI, that dust that blots out the stars in the Hubble picture will become glowing warm dust and visible as a source of bright emission in MIRI images. So the images will have as much detail, but a very different character.
As the sun rises over the Guiana Space Center, the team conducts final checks on the health and status of the Ariane 5 rocket and its payload. The James Webb Space Telescope, NASA's #1. As the sun rises over the Guiana Space Center, the team conducts final checks on the health and status of the Ariane 5 rocket and its payload. The James Webb Space Telescope, NASA's #1 science priority. The Webb telescope is designed to look back to a time when stars and galaxies were first forming, over 13.5 billion years ago. With its revolutionary design and capabilities, the Webb telescope is about to unleash a new dawn of discovery. Seconds before liftoff, the Ariane 5's liquid-fueled engine comes to full power, followed by the ignition of the two solid rockets. We have liftoff. The Webb telescope is finally on its way, the result of years of study and development by thousands of team members in the United States, Canada, and Europe. Webb's spacecraft ascends nearly vertically through the heavy lower atmosphere of Earth. As the rocket reaches maximum acceleration, the spent solid rocket motors are jettisoned safely into the Atlantic Ocean. Reaching the upper atmosphere where protection is no longer needed, the payload fairing is jettisoned and falls away. Accelerating through the atmosphere, the Ariane 5 rocket's first stage expends its fuel and shuts down. The empty first stage then separates from the upper stage. After first stage separation and before second stage ignition, the Webb telescope has a slightly downward trajectory as it speeds over the Atlantic Ocean. The upper stage motor ignites and the ascent to L2 resumes, never again to be interrupted. The exposed telescope is delicate and must be protected from the sun's fierce heat. To avoid overheating and damage, a carefully designed series of oscillations are performed that provide the necessary protection. Near the end of powered flight, the roll program stops and the launcher then assumes the proper attitude for separation. After separation from the Ariane upper stage, the Webb telescope continues its journey to L2 under its own power, taking the next step to its final orbital station 1 million miles from Earth. The Webb telescope is about to unleash a new dawn of discovery. The Webb telescope separates from the launcher's second stage. The white ring close to the Earth represents the Hubble Space Telescope's orbit, and the larger orbit is the geosynchronous orbit where most telecommunications satellites are located. The solar array is Webb's first deployment. When completed, all of Webb's electrical power needs are satisfied by the solar array for the remainder of the mission. The onboard control system continually monitors and updates the attitude to ensure power generation and thermal safety. To preserve the cleanliness of the mirrors, thrusters are located only on the sunlit side of the observatory. The trajectory is designed without employing a retrofire, which necessitates pointing the delicate telescope at the sun. If course corrections are needed, these velocity additions must be done early in the flight to most efficiently use the mission's limited precious fuel. After completing mid-course corrections, the Webb telescope passes the orbit of the Moon. Webb's initial transformation is the deployment of the sunshield pallets. The tower separating the telescope and instruments from the spacecraft and sunshield is next. Next, the aft flap deploys. This is key to managing momentum buildup in fuel consumption. This structure helps to balance the pressure from the sun's light on the Webb telescope around its center of mass. After the sun shield pellets reach their final positions, the membrane launch restraints are released. These have kept the sun shield membrane safely in place from final stowage at the Northrop Grumman facility in California through shipment and launch. The sun shield protective covers roll back, permitting membrane deployment. The covers over the core region release next. Then the mid-booms extend and the sun shield assumes its hexagonal tennis court-sized shape. It is now time to tension the sun shield membranes, each thinner than a human hair, pulling each of the uniquely sized and shaped layers to their optimal position. When deployed, the sun shield allows the telescope to cool to 385 degrees Fahrenheit below zero, cold enough to liquefy air, while the layer closest to the sun is almost 190 degrees Fahrenheit above zero, nearly the boiling point of water. It's of almost 600 degrees. Truly fire and ice. Once in the shadow of the deployed sun shield, the telescope and instruments continue cooling down to their final operational cryogenic temperatures. At the completion of membrane tensioning, the secondary mirror deploys into position and is latched rigidly in place. The aft deployable radiator releases and springs into position, allowing the instruments to radiate their waste heat directly into space and away from the telescope. Disposing of excess heat is crucial to the mission so that it does not overwhelm the faint infrared signals to be collected from the cosmos. Discoveries made by this observatory will rewrite textbooks, inspiring the next generation of future engineers and scientists. This revolutionary tool will provide an unprecedented view into the birth of the first stars and galaxies, unleashing a new dawn of discovery.